A major roadblock that new and seasoned software engineers face in advancing their careers is the technical interview process. Interview questions about data structures and algorithms tend to leave job candidates feeling frustrated and underprepared, since these concepts are weighted heavily in interviews, but many roles don't actually require their use. To help you put your best foot forward at your next big interview, I'll show you how to create and use 3 Python data structures that commonly appear as interview questions: stacks, queues, and deques. I'll compare and contrast these data structures in detail, and also demonstrate how to implement each one in an object-oriented way. Hi, I'm Erin Allard, and I'm a software engineer focused on Python and Django. I'm passionate about helping people advance their software engineering careers by coaching them through the technical interviewing process. Join me in my LinkedIn Learning course for a head start on implementing 3 of the most fundamental data structures using Python. In order to get the most out of this course, there are a few concepts you should know. The first is Python's built-in list data type. Specifically, knowing about the list data type's built-in append method, pop method, insert method, and how to index into a list. You'll also want to know about classes in Python, how classes have attributes, methods, and how to instantiate objects. You'll also want to know at least the basics about how to calculate runtime, specifically constant runtime, also called O of 1, and linear runtime, also called O of n. If you need a refresher on any of those concepts, here are a couple LinkedIn Learning courses you can check out. The first one, called Python Essential Training, has a really great chapter on classes. The second one, called Programming Foundations Object-Oriented Design, gives a great overview about object-oriented programming. You can follow along with me by downloading Python 3. I'll be coding in Atom, which is my favorite text editor, but you can use whichever one you like. I'll be running my Python files from the terminal, and you can use your favorite CLI tool. I recommend you create your own Python files on your machine and code with me throughout the course. I've also made my completed Python files available for you to download in case you want to use them as a resource. Before we dive into stacks, queues, and deques, we should understand more about what abstract data types are. Abstract data types are a theoretical computer science concept. They simply describe what kind of data a data structure can hold and what operations are allowed on that data. If you were creating an entirely new abstract data type from scratch, you could decide what these operations would be. But since we're working with stacks, queues, and deques, which are already defined and understood in the computer science community, we'll stick to the basic operations that already exist for those abstract data types. When we think about the purpose of an abstract data type, we're not at all concerned with how we'd code it. We just want to understand how we should be able to interact with it in the way we'll need to. Again, an abstract data type just expresses an idea. Abstract data types aren't specific to a certain programming language. You could implement one in many different languages. Abstract data types are always talked about from the perspective of the person who will be using them, not from the perspective of the person who is going to implement it. There are 2 styles for spelling out how an abstract data type works: the imperative style and the functional style. In the imperative definition of an abstract data type, we think of the abstract data type as mutable or changeable. We allow the same abstract data type to be in different states at different times. Since operations on the abstract data type can change its state, the order in which those operations are executed is important. This is the style we'll be using throughout our course. The other style is called the functional style. In the functional definition of an abstract data type, we think of the abstract data type as immutable or not changeable. It has a separate entity of the abstract data type for each state that it can be in. This means that an operation that modifies the abstract data type is operating on the present state and returning an entirely new state as a result. In this way, the original abstract data type is never changed. Consequently, the order in which the operations are executed in the functional definition doesn't matter, since no operation is changing the present state. There are a couple advantages to thinking about data using an abstract data type. The first is abstraction. Regardless of how the abstract data type is implemented to eventually become a data structure, the abstract data type will have certain predictable properties and allowed operations that we specify at the outset. All a user of the abstract data type needs to know is the type of data it requires and the allowed operations on it. An understanding of the implementation is not necessary in order for the user to make use of the resulting data structure. The second advantage is consistency. A person who is using the interface of a data structure as specified by its abstract data type doesn't need to understand the implementation. Consequently, the implementation of that data structure could change, and as long as the new implementation supports the existing interface, the user doesn't need to change their own code. The next thing we need to understand is data structures. A concept that goes hand in hand with abstract data types is data structures. A data structure is a concrete implementation of an abstract data type that helps you store and organize data in memory. Data structures are always talked about from the perspective of the programmer who is coding them. For every operation that is allowed on an abstract data type, we have one method or one function that is defined by the data structure's class. There is often more than one way to implement an abstract data type as a data structure. In the rest of the course, we'll talk about how to create data structures for stacks, queues, and deques. Now that we understand the difference between abstract data types and data structures, let's talk through what makes the stack abstract data type unique, and also touch on the basic functionality we need a stack to have. Here's a high-level definition of a stack. It holds a collection of items in the order in which they were added, and you can only add items to and remove items from the top of a stack. If you think of a stack as a stack of pancakes, you can only add to the top of the pancake stack and remove from the top of the pancake stack. We say this is last in, first out, because the most recent item you add is the one that's going to get removed next. Another way you may hear this phrased is LIFO. It follows from this example that the order in which pancakes were added to the stack is preserved. In other words, you can't take the bottom pancake without considerable effort and a potential mess. When it comes to implementing a stack, our first consideration is whether or not Python has a built-in data type that we could use behind the scenes. We need a mutable data type that holds an ordered collection of items. A list fits this requirement perfectly. So that's great. Python has a built-in data type we can use behind the scenes. The basic functionality for a stack is getting items into and out of the list we use to represent that linear data structure. When we code our stack class, we're going to use the right side of a list to represent the top of a stack. You can also think about this location as the end of the list. The reason we choose the end of the list has to do with runtime. Removing the last item of a list is done in constant time. So is appending an item to the end of the list. We may also want to know whether or not a stack is empty, how many items are in it, or which item is at the top. We'll create a method for each of those capabilities later on. We talked about some operations we'll need to be able to make on a stack. In terms of the data the stack will hold, it can be any data type that can be stored in a list. Further, the stack is what's called a limited access data structure. This is because we can only access data from one place, the end of the list. A couple examples in which stacks could be used in your everyday life are a linter in your text editor, which is able to tell you if you're missing an opening or closing symbol, or reversing the characters in a string, which is a common interview question. A final note about stacks is that they have a unique property about them, and that is that they are also recursive data structures. A stack is either empty or it consists of a top item, and the rest of which is a stack. We won't discuss recursion in this course, but knowing that a stack is a recursive data structure may come in handy in an interview. Now that we've discussed the stack abstract data type, we know what we want the stack to do, and we can start to stub out a stack class and its methods. First, we need to define the class itself. So let's call it stack. We talked about how we need to use a Python list behind the scenes to represent the stack. So we can create an init method to do that. And we'll create a variable called self.items and initialize that to our empty list. The other basic functionality we need is we need to be able to add an item to the stack. The word we use for that is push. And we'll also need to pass into push the item that we want to add to the stack. Since we're just stubbing things out now, we'll use the pass keyword to remind ourselves to come back to that later. Just like we added, we also need to be able to remove an item from the stack, and we use the word pop for that. Now, because the list's built-in pop method always returns the last item of the list anyway, we don't need to specify an index or an item that we want to remove. That will take care of that automatically for us. Building on top of these two basic things, there are three other things we probably want to be able to do. The first is we'll want to peek, perhaps, at what the next item is that's going to be removed. We may want to know how many items are in the stack, and the word we use for that is size. And lastly, we may want to know whether or not the stack is empty. So we've stubbed out all of the methods for our stack class, and we'll start filling them in. The first method we can flesh out is this push method, and this is the method that's going to allow us to add an item onto the stack. We've already specified the item here, and so now we just need to append that to the list that we've created above. So we'll just say self.items.append, and we'll pass in the item that we want to add. Now, since this is a learning exercise, I do think it's a good idea that we add doc strings to each of these methods. So I'm just going to write a brief note about what this method does. So I'll say it accepts an item as a parameter and appends it to the end of our list. And it returns nothing. Now, we talked earlier about how appending to the end of a list happens in constant time. So let's make a note about the runtime as well. And the reason I think it's important to do this is data structures are often covered in interviews, and typically your interviewer will ask you about the runtime. So I'm just going to say that the runtime for this method is O of 1, or constant time, because appending to the end of a list happens in constant time. And the reason this is constant time is what's actually happening is Python is going directly to the last item of the list. It's indexing to the last item, and indexing into a list, as you may know, happens in constant time. So there we go. To test to make sure that my new push method actually works, we can run that Python file interactively in the terminal. I'm using Python 3, and the way that I can run that is like this. And so now all of the code that I just wrote is available in my terminal. So I can create my own stack object. And at this point, the only method that we have is the push method. So I can try that out by passing in apple, a string containing the word apple. Now remember that the variable that we're using here is items. So I can go back to the terminal, type in mystack.items, and that will show me now what is in my list. If we add another item, let's say banana, so we'll do mystack.push, and we'll pass in a string containing the word banana. I expect that banana will appear to the right of apple. Let's see if that's correct. It is. And the reason this is the case is because we always consider the right side of the list to be the top of the stack. And we can only add to and remove from the top. So every time we add something else, it's always going to show up on the rightmost side of that list. We'll do myStack.items again to check, and there we go. The second method we can work on is our pop method, and this is the method that's going to allow us to remove an item from the top of the stack. Now we know already that the list data type has a built-in pop method, so we're just going to make use of that. So we will return whatever value is given to us by self.items.pop. Now, we don't have to specify an index here because we always are going to be wanting it to return us the last item from the list. That's how the pop method works. If you don't give it any parameters, it will always return the last method. That's pretty much it. Let's add another docstring as we did for push. So what does this method do? This method returns the last item. We should say removes and returns the last item from the list, which is also the top item of the stack. And just as we did before, we should talk about the runtime here as well. And the runtime is also constant time, just as it was for push. Because really all we're doing is we are indexing to that last item in the list and then returning it. So all it does is index to the last item of the list. Let's go ahead and test this out in the terminal. I will again run Python 3 interactively, and I will create my own stack object. Now at this point we have two methods. We have push and pop. And I want to try the pop method without having pushed anything first to see what's going to happen. So I'll just do myStack.pop, and I'm kind of expecting an error to happen here. And that's what happens. The index error is that I'm trying to pop from an empty list, or in other words, I'm trying to remove something from a list that doesn't have anything in it. Now what this tells me is this is an opportunity to go back into my code and create a condition to look for this. Let's add in that condition statement here. So what I want to say is, as long as there are items in the list, give me the last item. To do that, Pythonically, I can say if self.items, and this basically means if there is something in self.items, return the popped value. Otherwise, we may want to just return none. So I'm going to save this. We'll go back to our terminal. I'll have to restart my interpreter, but that's okay. I'll do Python 3-i and then the name of my file. Okay, so we'll recreate our stack object. And now let's try calling that pop method again. Cool, this worked. It basically returned none. So now that we've accounted for that scenario, let's push an item. We'll push apple to be consistent with our example. And I also want to push banana. And now when I call myStack.pop, what I should be getting is banana, because remember, in our code we said not only remove that last value, but return it as well. And so that's why it shows up there in my terminal. If we look at the items attribute again, we should only see apple now because banana should have been removed entirely. And that's what we get. We now have the basic functionality for our stack class because we have coded the push and pop methods. So let's move on to these other three extra methods, if you will. The next one is called peek. And what this is going to do is show us what the next value is that's ready to be popped. So in other words, this should show us the item that's on the top of the stack. We want to return that item as well. So all we need to do here is we just need to return whatever value or whatever item is in the last index of the list. So that would be self.items, and then we can index into the negative first position. So I'm going to save this, and we'll go back to the terminal here. fire up the interpreter. I'm going to create another stack object. And I'll just push one thing onto it this time. I'm going to stick with our apple example. So now, if I call peak, I expect it to show us apple. And it does. But what would happen if I tried to call peak on an empty stack? We can test that out ourselves. So I'm going to pop off apple. I can double check that my stack is empty now, and it is. So if I call myStack.peak, at this point, I get an error. The reason I get an error is because I'm trying to index into the last item of a list, but the list doesn't have anything in it. So let's add a condition for that into our code here. It'll be pretty similar to the condition that we used in our pop method. I want to say as long as there are items in that list, so if self.items, then return the last item in the list. Otherwise, just return none. So I'll save. Let's try this one more time. Forgot to rerun my interpreter here. There we go. So my stack equals, and we don't have to add anything this time, right? Because we just want to test what happens to our peak method on an empty list. We should get nothing, and that's what happens. Cool. So let's go back to our code and we'll add in the docstring and note about the runtime as we have been. All right, so this method returns the last item in the list, which is also the item at the top of the stack. Clean up my capitalization here. There we go. And let's make a note about the runtime. So again, since all we're really doing is indexing into a list, and we know that indexing into a list is done in constant time, that's the only thing we need to say here. So this method runs in constant time because indexing into a list is done in constant time. Since we're representing our stack with a list, in order to figure out how many items are in the stack, all we need to do is use the list's built-in length method to find the length of the underlying list. So we'll come into our size method here, and really all I need to do is just return the result of calling that length method. So we'll do basically find the length of self.items. I'll save this and then go back to my terminal and run the file, interactively of course. And here I'm going to create my own stack object. And before I add anything to it, I want to check my size method, make sure I've coded it properly. So we'll do myStack.size, and I expect to get 0. Yep, that's what I get. So now let's push something onto the stack. We'll do apple again. Okay, and if I call the size method again, I expect that it would return 1. And that's what I get. So let's go back to the code here and we'll add our docstring and runtime note as we have been. So what does this method do? This method returns the length of the list that is representing the stack. All right, now let's talk about the runtime. So the runtime of finding the length of a list is constant time. And therefore, this method is also going to be running in constant time. So we'll say, in summary, this method runs in constant time because finding the length of a list also happens in constant time. The last method we'll add to our stack class is the isEmpty method. This should return a Boolean value describing whether or not the stack is empty. To do this, all we need to do is test for equality between our stack instance, which is represented as a list, and an empty list. So in code that looks like return self.items double equals empty list. If our list is equivalent to an empty list, that would return true. But if our list is not equivalent to an empty list, that would return false. So I'm going to save our file and we'll go back to the terminal. I'll fire up the interpreter here, create our stack object, and let's get right to testing this new isEmpty method. Now, the first time we run this after having created our stack object, we expect that the isEmpty method would return true, which it does. So let's now push a string with apple in it onto our stack. We can double check that here. My stack.items, a list with only apple in it, which is what we expect. And now if we do myStack.isEmpty, we should get false. Yep, that's exactly what we get. Great. So let's go back to our code file and add the docstring and runtime note. And this method simply returns a Boolean value describing whether or not the stack is empty. So this method returns a Boolean value describing whether or not the stack is empty. And such a simple test of equality like this does happen in constant time, like all of our other methods, and so we'll make a note to that effect. Testing for equality happens in constant time. There we go. Now that we've implemented the stack data structure using Python, let's put it into practice. In this challenge, your prompt is to create a function that takes in a string of symbol pairs as a parameter. The function should return true if the symbol string is balanced or false if it isn't. Here's what we mean by a symbol string. The string should only contain opening and closing symbols like open and close parentheses, open and close square brackets, or open and close curly braces. This is to mimic what happens in your text editor when the linter is checking for whether or not you remembered to close all of your opening symbols. In order for symbols to be balanced, each opening symbol should also have a closing symbol, and the symbols must be properly nested. You should, of course, make use of a stack in your solution. Here are some examples of what I mean by balanced symbols. And here are examples of unbalanced symbols. It's pretty obvious. Feel free to come up with your own solution, and then I'll show you how I approached it. Let's talk through one possible solution to the stacks challenge. The approach I took was to fail fast. I chose to return false as soon as I hit a mismatch. If I got through the whole input string and the stack was empty, then I returned true because that would mean that all the symbols were balanced. If I didn't encounter that situation, I would return false. I decided to loop through the symbols of the input string. If one of those symbols was an opening symbol, I would push it onto my stack. If the symbol that I got to was a closing symbol, then I would check to see if the top item on the stack was its matching opening symbol. If they were a matched pair, the symbols would be balanced, and so I could move on to the next symbol in the string. If they weren't a pair, I could return false immediately. By the end of all that iterating, if I had made it through the whole input string and the stack was empty, I could return true because I would know that all of the symbols were balanced. But if there was still at least one item in the stack, then the symbols were not balanced because at least one would not be matched, and so I would return false. Let's go to the code to see how I implemented all of this logic. Here's the code I wrote to approach this solution. I knew that I would have to use a stack class exactly as we have earlier in the course, so I simply duplicated that code. I won't spend any time going through it here. Instead, I'll move on straight to the logic. I created a function called matchSymbols, which takes a parameter called symbolString. Within this function, on line 18, I created a dictionary called symbolPairs. All of the keys are strings that have one character inside of them, and these are all of the opening symbols. Each of these opening symbols is mapped to a value, which is a string containing its matching closing symbol. On line 24, I created a variable called openers because I knew later on in my code I was going to need to check if each symbol was an opening symbol or not. To create the openers variable, I simply called the dictionary's built-in keys method on my dictionary. I did that because all of the keys are all of the opening symbols. On line 25, I instantiated my stack object and called that myStack. On line 27, I created an index and initialized it to 0 because I knew I was going to use it in my while loop so that I could loop through the symbol string. I began my loop on line 28, and on line 29, I'm taking whatever symbol exists in the string at the index that's given in the loop. On line 31, I'm checking to see if that symbol is an opening symbol. If it is, I'm pushing that opening symbol onto my stack in line 32. If the symbol is a closing symbol, then I have some other logic I need to work through. If the stack is already empty, the symbols aren't balanced. In that case, I can return false and fail fast. But if there are still items in the stack, I need to check the next one to see if it matches my symbol or not. I start to do that on line 41, where I pop the topmost item off of my stack and save it into a variable called topItem. On line 42, I check to see if that topmost item of the stack is a matching pair to the symbol that I'm currently working with from my input string. If they're not, I return false right away. If they are, I simply increment my index and start my loop all over again. On line 47, if I can get through the whole input string without returning false, the next thing I need to do is check whether or not my stack is empty. If it is empty, that means all of the symbols were balanced and I can return true. But if it's not empty, it means the symbols were not balanced and I need to return false. You can see at the bottom here I have two test cases. The first one on line 52 does have balanced symbols inside the input string, but the second test case on line 53 does not have balanced symbols. So when I run this file in the terminal, what I expect to happen is the test case on line 52 will print true and the test case on line 53 will print false. Let's try that out. That's exactly what we get, which tells me that it works. As you know, there are several ways this could have been solved, and this was the approach I chose. Let's talk about what makes the queue class unique, especially in comparison to stacks. Here's a high-level definition of what a queue is. Queues hold a collection of items in the order in which they were added. Items are added to the back of a queue and removed from the front of the queue. If you think of a queue as a line of customers, a customer adds themselves to the end of the line and eventually leaves from the front of the line. This is called first in, first out, or FIFO. Note that this is subtly different from stacks, which are last in, first out. Queues also preserve order, so when you think about people joining a line, the order is preserved there as well. Just as we did for the stack class, we can see if there is a built-in data type we could use to implement the queue behind the scenes. Again, we can use a list, because a list is an ordered collection of items that we can modify. When we code our queue class, we're going to use the right side, or end, of a list to represent the front of the queue. We do this because we can remove an item from the end of a list in constant time. So if we make the end of the list match the front of the queue, we can always remove items from the queue in constant time. This means we'll have to use the left side of the list as the rear of our queue. Consequently, we'll be adding items to the queue in linear time. It's linear time because when we insert an item into a list's 0th index, it causes all the other items to have to shift one index to the right. The larger our queue gets, the longer it will take to enqueue an item into it. We could have arbitrarily chosen to represent the queue as a list where we remove from the left side in linear time and add from the right side in constant time. we'd still wind up with one operation being O of 1 and the other operation being O of n. The basic functionality for a queue is getting items into and out of the list we are using as a representation of the queue. When we're talking about adding items to this list, the word we use is enqueue, and when we're talking about removing items, the word we use is dequeue. Any data type that can be stored in a list can be stored in a queue. And we call a queue limited access because we can only access the data from one place, which is the front of the queue. We may also want to know whether or not a queue is empty, how many items are in it, or which item is at the front of the queue. We'll create a method for each of those capabilities later on. The queue linear data structure is especially useful when we need to process information in the same order in which the information became available. For example, a print queue, so that documents are printed in the order in which they were sent to the machine. Queues have another unique property about them, and that is that they are also recursive data structures. A queue is either empty or it consists of a front item and the rest of which is also a queue. We won't discuss recursion in this course, but knowing that a queue is a recursive data structure may come in handy in an interview. Let's stub out our queue class and its methods. We can call our class just queue. And we talked earlier about how we're going to represent our queue as a list. So in our init method, we can do, again, like we did for stacks, self.items equals an empty list. Now, our basic functionality is we need to get things into and out of our queue. And the words that we use for that are enqueue for adding and dequeue for removing. So first we can stub out the enqueue method. And we will have to pass in as a parameter the item that we want to add to our queue. And we'll just write pass here for now. And then we can move on to the dequeue method. And we don't need to pass in an item here because remember, we're always going to be popping off the end of the list, which automatically takes the last item of the list for us. In addition to the basic functionality of enqueuing and dequeuing, we may also want to know what is the next item in the queue that's going to be removed. And we call that peak. And we'll just pass that for now. Another thing we might want to check is the size of our queue, which basically means the length of the underlying list. And finally, we might want to know whether or not the queue is empty. I'll save that file. Let's start coding the minimal functionality we need for our queue class. We'll start with the enqueue method. Again, as we talked about, we have to pass in as a parameter the item that we want to add into the queue. And in the body of our method, we're going to need to do something with that. Now, we know that we're going to be operating on our empty list, which is called items. But instead of appending the item to the end of the list, like we did for a stack, we want to now insert the item into the 0th index of the list. And we talked about how the reason we do that is because we want to sort of save the end of the list for popping and use the front of the list for inserting. So I'll save that. We can go back to the terminal. I'll start up the Python interpreter here, and we can try this out. I'll create my own queue object first. And next, I will enqueue an item into it. So my queue.enqueue, and let's add in a string containing the word apple. If I want to check that it worked, I just need to look at the items attribute. So my queue.items gives a list that has the string apple in it. So we know it works, but let's double check to make sure that the enqueue method is actually inserting items into the 0th position of the list like we wanted it to. So I will run the enqueue method again, this time with the string banana. And what should happen when I double check the attributes is banana should be appearing to the left of apple. And that's exactly what happens. Now we can go back to our code file and enter in the docstring and the note about runtime. So this method takes in an item and inserts that item into the 0th index of the list that is representing the queue. Because we're always inserting into the 0th element of the list, it forces all of the existing elements one index to the right. So if we have n number of elements in our list, the runtime would be O of n. Let's paraphrase that here in our docstring. We'll say the runtime is O of n, or linear time, because inserting into the 0th index of a list forces all the other items in the list to move one index to the right. I'll just make an adjustment here for my spacing, and we're all set. Now that we've coded the enqueue method, which helps us get an item into the queue, let's code the dequeue method, which will help us get items out of the queue. Now, since we are using a list to represent our queue, and we are representing the front of the queue with the end of the list, if we use the list's built-in pop method, we'll always get back the frontmost item of the queue because the pop method always returns the last item in the list. So let's go ahead and do that. We'll return self.items.pop. I'll save this, and we can go to the terminal and test this out. Let's get the interpreter open, and I'll create a queue object. And let's add something to our queue here. So we'll do myqueue.enqueue, and we'll add the string apple. Okay, and if we check the myqueue.items attribute, we should get a list that has apple in it. Yep, we do. Now let's dequeue this. Let's get apple out of there. So we'll say myqueue.dequeue. We should get apple back to our screen. Yep. If we run myqueue.items again, we get an empty list. Let's test the case where we try to dequeue from an empty list. So if I do myqueue.dequeue, I'm probably going to get an error. Yep, I get an index error. And it's saying basically that I can't pop an item from a list that has no items. So we can go back to our code and add a little conditional statement to handle that. We can say if self.items, meaning if there is something in the items list, then we'll pop something from it. Otherwise, we'll just return none. Let's go back to the terminal and try that out. So I'll have to exit the interpreter and restart this, and recreate my queue object. And straight away, I'm just going to try to dequeue from this. And I should not get an error this time. It should just return none. And that's what happens. We can double check by saying myqueue.items. It should be an empty list, which it is. Great, so we've handled that situation. Now we can go back and add the docstring and our note about the runtime. Let's summarize what this method does. So the dequeue method returns the frontmost item, or we should say returns and removes the frontmost item from a queue. Returns and removes the frontmost item of the queue, which is represented by the last item in the list. As for the runtime, when we append to or remove from the last item in the list, what we're effectively doing is indexing to the last item of the list. And that happens in constant time. Therefore, the dequeue method also happens in constant time. So we'll just say the runtime is O of 1, or constant time, because indexing to the end of a list happens in constant time. We've covered the basic functionality with enqueue and dequeue, but what if we just want to look at what the next item in the queue is that's going to be removed next? We can use our peek method for that, And basically, all we need to do is just return the last item in the list, because that last item in the list is the item that's going to get removed next. So in terms of code, we can simply say return self.items at the negative first index. We'll start with that. So I saved the file. We'll go to the terminal and we'll get the interpreter started. I'll create my own queue object. And let's try this just as the object is. We haven't added anything to it yet, which means that items should be empty. And it is. So if we say myQueue.peak, we get an error. List index out of range. So what's happening is we're trying to access the negative first index, but we don't even have anything in the list to index into. We can handle this situation in our code. What we want to say is, as long as there are items in the list, show me the last item in the list. The way we can do that is simply if self.items, return the last item. Otherwise, if the list is empty, we'll just return none. Okay, so I'll save that. We'll go back to the terminal and I'll restart everything again. So we'll do python 3-i and then the name of our file. I'll create another queue object. And this time, when I call peak, it should just return none because we haven't added anything to our list yet. And that's what happens. So now let's enqueue something. We'll enqueue the string apple. And let's also enqueue the string banana. Just double check that these got added the way we expected. Yep, that makes sense. We're adding from the left and removing from the right. So now when we call the peak method, we should see apple. And it is. Now the difference between peak and dequeue is that peak doesn't remove anything. It only shows it to us. So we can double check that nothing has been removed by looking at the items again. And it's just fine. Let's go back to our code and add a docstring and details about the runtime. In summary, the peak method returns the last item in the list, which represents the first or the front item of the queue. So we'll just say that. Returns the last item in the list, which represents the first item, well, let's say frontmost item in the queue. And again, since we're just indexing to the last index of the list and returning the value we find there, nothing too complicated, the runtime's going to be O of 1 or constant time. So the runtime is constant because we're just indexing to the last item of the list and returning the value found there. I'm going to change my spacing here just a little bit. And there we are. The two remaining methods we have for the queue class, size and isEmpty, are exactly the same as the size and isEmpty methods that you would use for a stack. Let's code these and then we'll test them out in the terminal. Now when we want to find size, what we're talking about is really the length of the list. So we can simply return the length of self.items. And even if items is empty, it should still return 0. So we don't need to account for that situation. Let's add our docstring, and the summary here is simply returns the size of the queue, which is represented by the length of the list. And the runtime would be O of 1, which is also called constant time because we're simply returning the length. Let's move on to the isEmpty method. For the isEmpty method, we just want to know whether or not the queue, or the list that's representing it, is empty. The way we can do that is by returning a comparison of the list we have to an empty list. So we would simply say return self.items double equals an empty list. And this would return a Boolean value, either true or false. True if items is an empty list, false if it's not. We can add our docstring here, add our runtime note, So simply returns a Boolean value expressing whether or not the queue, well, let's say whether or not the list representing the queue is empty. I'll adjust my spacing here. And a simple check for equality like this will run in constant time. Looks like I've got a little capitalization problem here. I'll fix that. Now let's test these out in the terminal. We can start the interpreter, create our own queue object as we have been. Now before I even enqueue anything, I can try both of the methods I just created. So first, let's do size. We expect that this should give us 0 because we haven't added anything to the list yet. And that's what happens. Let's try the isEmpty method. This should return true because we haven't added anything yet. And that's exactly what happens. Now let's enqueue something and test these one more time. We'll enqueue the string apple. And I'd just like to check, make sure it worked. It did. So let's now do myQueue.size. And this time it should return 1, which it does. And lastly, we'll try myQueue.isEmpty, and this should return false, which it does. Now that we've gone over implementing queues in Python, let's put this new skill into practice with a queues challenge. The prompt is to create 3 classes that together model how a printer could take print jobs out of a print queue. There are a few requirements. The first is a class called printQueue that follows the queue data structure implementation. The second requirement would be a class called job that has a pages attribute, and each job can have 1 to 10 pages. You can assign this number randomly in your program. The job class should also have a print page method that decrements pages, and a check complete method, which will check whether or not all the pages have been printed. The third requirement is a printer class. The printer class should have a getJob method that makes use of the queue's built-in dequeue method to take the first job in the print queue off of the queue. Make sure you account for the case where printQueue.items is empty, or else you'll get an error. Go ahead and give this a try, and then I'll show you how I solved it. Now I'll share the approach I took to solve the queues challenge. For the printQueue class, I made that identical to the data structure we created in our queue chapter. I knew that the job class should have information about how many pages are left in the job. If I printed a page from the job, I decremented the page count. When the job got to a point where it had 0 pages, I knew that printing was complete. As for the printer class, I knew it should carry information about the job that it was working on. I also knew that I was going to have to figure out how to make the classes talk to each other, because the printer needed to get the next job by dequeuing from a non-empty printQueue object. Another example of how I needed to get the classes to talk to each other was that I knew I would need to use job.printPage and job.checkComplete within my printer class. Let's take a look at the code I wrote to make all of this happen. I'm going to run my file interactively so that I can play around with the classes I made. The first thing I want to do is I want to create an object for each of the classes. So first I'll create a job. I'll just call it job1. And then I'll create a print queue, and I'll call that print_queue. And that will be an instance of my print queue object. And lastly, I'll create a printer, or a printer instance called printer. Okay. The first thing I need to do is I need to get that job1 into my print queue, because right now my queue doesn't have anything in it, so all of the methods I wrote aren't super useful. In order to get something into my queue, I need to enqueue an item into it. Now, because print queue or print_queue is a print queue object, I have the enqueue method available to me. So if I call the enqueue method on print queue, and I pass in the item, which is job 1, so I'm passing in an entire job object to my print queue, I now have something in my print queue. And I can test that out by looking at the items attribute. And here you can see the representation for that object. Now that I have something in my queue, I can think about having my printer object pull that thing out of the queue. So if I call the getJob method I created on my printer object, that should give me what I want. The thing I need to remember here is that I have to pass in as a parameter to getJob the print queue that I actually want to pull a job from. And that print queue I want to pull a job from is what I stored inside of print_queue. One way that I can verify this worked is I can look at the items again. And since the getJob method, we can go back to our code here. Since the getJob method is using the dequeue method, which means it's popping the last item off of the list, I should now have an empty list. And I do, so that's great. There's a method I created that I haven't tried yet, and that is part of the printer class. I haven't tried yet printJob. And the cool thing about running this method is that it will also run the print page and the check complete methods too, which are up here in the job class, and I haven't tried those either. So by calling the printJob method, I can also try out these other two. Let's go back to the terminal and do that. Now, because the printJob method is part of the printer class, I need to call it on my printer object. So I'll say printer.printJob, and I need to pass in a parameter. We'll go back to the code here. I need to pass in the job that I want to print. This is currently represented by this self.currentJob. We know that's the case because a moment ago when we called getJob, what we actually did was we pulled that job out of the queue and assigned it into a variable inside of the printer class. So here, I'm just going to access that attribute by saying printer.currentJob. Printing complete. And that is the message that should get returned if the checkComplete method returns true, which it does. So now you've seen the code that I wrote, and together we've manipulated the objects that I instantiated from my classes, and we've verified that all of the methods work. This is the approach I took, but there are certainly other ways you could have gone about this. Let's talk through what makes the Deque class unique in comparison to other linear data structures, and also touch on the basic functionality we need a Deque to have. First of all, Deque stands for double-ended queue, where we take the D, the E, and the first three letters of queue and put them all together to create this new word called Deque. A high-level definition of a Deque is that it's an abstract data type that resembles both a stack and a queue. Deques can hold a collection of items, and order is sort of preserved in a Deque. You'll see soon why I use the phrase sort of. In a Deque, you can add items both to the front and to the back, and you can remove items from the front and back as well. When it comes to implementing a Deque, our first consideration is whether or not Python has a built-in data type that we could use behind the scenes. Just like for the stack and queue data structures, we can use a list to implement a Deque because a list is an ordered collection of items that we can modify. Here you can see we have a list with 5 items in it. If we imagine that we could bisect the list, you'll see that the right-hand side is very similar to a stack because we would add and remove from the end of this list, or where the 4th index is. If this were a queue, we would also be removing an item from the queue on this side. On the left side, if this were a queue, we would be adding here into the 0th index. The only other thing we need to accomplish is being able to remove from the front, which would be a method that would be unique to the Deque class. Because we can add and remove items on both sides of a deque, we need to use method names that specify which end of the deque the operation is happening on. So, we'll use add front and add rear, and remove front and remove rear to make that distinction. We may also want to know whether or not the deque is empty, how many items are in it, or which item is at either end. And we'll create a method for each of those capabilities later on. A queue uses a first in, first out, or FIFO model, and a stack uses a last in, first out, or LIFO model. An interesting thing about the deque class is that it can use either of those models or both of those models at the same time, since we are allowed to add and remove from both ends. It's up to the programmer, though, to enforce those qualities on either end of the deque if they choose to do so. We can arbitrarily choose which end of the deque we want to be at the front and which we want to be at the rear, since there isn't any runtime advantage of choosing one side over the other side to be the front. The reason is that whether we want to add or remove from the left side of the list or add or remove from the right side of the list, we're going to be in constant runtime or linear runtime, depending on which side we choose to be the front. Any data type that can be stored in a list can be stored in a deque. And a deque is also a limited access data structure because we can only access the data from either end. The deque data structure is a solid way to approach the solution for a common interview question, which is to check whether or not a string is a palindrome. A palindrome is a word that is spelled both the same backwards and forwards. So the deque data structure is a good approach for this problem. Let's stub out the code for our deque class. So we'll define our class and give it the name deque. And we talked earlier about how we'll use a list behind the scenes to represent the deque. So let's create our init method. And within our init method, we will create an items variable and initialize that to an empty list. And now we need to get into the basic functionality of the deque, which is adding items to it and removing items from it. Now remember, with a deque, you can add to either side and remove from either side. So for each of those methods, we're going to have to specify the location of the deque that we want to be adding or removing from. So let's start with add front. And for this, we'll pass in self and the item that we want to add to the deque. And we'll just pass for now. And next, let's add the add rear method. Again, we'll need to pass in that item that we want to add. And we'll do something very similar for the removal methods. We'll do remove front and remove rear. And notice here again that we don't need to specify which index we want to remove because we're going to be using the list's built-in pop method. And we'll talk more about that later. Now we can get into the non-essential but still helpful methods like peek, size, and isEmpty. With the peek method, we will have to specify which end of the deque we want to be looking at. So again, we'll do the front and the rear. And the size and isEmpty methods for a deque are logically identical to the size and isEmpty methods for stacks and queues. And now lastly, we'll do the isEmpty method. There we go. As you can see, the deque class has quite a few more methods than a stack or a queue class would, and that's because, again, we need to always specify which end of the deque we're working with. It's time to start coding the logic for all of these new methods that we've stubbed out for our deque class. Let's start with the methods that have us adding items into the deque. We can start with add front. Remember that we're using the left side of the list to represent the front of the deque. So when we add an item to the list, we're going to be inserting it into the 0th index of the list. This is exactly how you would enqueue an item onto a queue. So we'll use the exact same logic. For add front, we'll do self.items.insert, and here we need to pass in both the index and the item that we want to insert. For adding an item to the rear of the deck, which is represented by the right side of the list, we simply need to append the item we want to add onto the list. For that, we can do self.items.append and pass in the item like that. I'll save this file and go to the terminal, where I'll start the interpreter. And I've chosen to name this Python file deques.py. First thing I need to do is create my own deque object. I'll call that my_d for short. And to start us off, I can look at the items attribute and just make sure that that is giving us an empty list, which it is. So let's go ahead and make use of the addFront method first. I'll do myd.addFront, and here I'll pass in a string containing the word apple. I can double check that worked by looking at the items again. And here we have a list with just one thing in it. Now addFront, if you recall, is inserting the item into the 0th index. So if I were to call addFront again, the item that I'm adding the second time should appear to the left of apple. Let's try that out. We'll do myd.addFront, and this time I'll pass in a string containing the word banana. If I check myd.items again, cool, that's exactly what I get. So we know that the addFront is working properly. Let's try the addRear method. We'll do myd.addRear, and this time I'll pass in a string containing the word carrot. Check the items, and carrot should now appear to the right of apple. Cool, this works. We can go back to our code and add a little docstring note just describing what this method does and what the runtime is. Here I'm going to say takes an item as a parameter and inserts it into the 0th index of the list that is representing the deque. Now, because we're inserting into the 0th index of the list, that means every other item that may already be in the list is going to have to shift one index to the right. Consequently, if there are n items in the list, the runtime is going to be O of n. So let's make a note to that effect. The runtime is linear, or O of n, because every time you insert into the front of the list, all the other items in the list need to shift one position to the right. Okay, and we can do a similar docstring for addRear. It'll be a little bit different, of course, because the logic is slightly different. But we can say takes in an item as a parameter and appends that item to the end of the list that is representing the deque. The runtime here is a bit better. It's constant time, because appending to the end of a list happens in constant time. And there we go. Our first two methods are complete. If we want to remove something from the front of our deque, which is represented by the left side of our list, we can use the list's built-in pop method and simply pass the index that we want to remove into that pop method. That would look like something like this. Return self.items.pop, and we'll pass in the 0th index to that pop method. The remove rear method is almost identical. The only difference is that we don't have to pass in that 0th index because the built-in pop method by default will always return and remove the last item of a list. Let's save this and we'll go back to the terminal and test this out. First thing I'll do is create my own deque object. And let's add a couple items here. We'll do addFront apple and banana. And how about one more? We'll add carrot. And just for fun, we can check our items attribute. And that's exactly what we get. We can see that every time we've been adding a new string to the front of the list. Let's try out our new remove front method. If we do myd.removeFront, what I expect to happen is the string caret should be removed and returned back to me. Okay, there it is returned back to me. Let's make sure it was also removed. If we do myD.items, we should see just a list that has banana and apple in it. And that's what we get. So remove front works just fine. Let's try remove rear. If we do myD.remove rear, what I expect to happen is apple should get removed and returned back to me. There it is returned back to me. And if we do myD.items, we should get now a list that only has banana in it. And that's what we get. So we know that our code works. Let's go back to the code file and add a quick docstring for each of these. For our remove front method, all this method does is just remove and return whatever item is in the 0th index of our list. And that left side of the list represents the front of the deque. Just like with our add front method, which was in linear time, the remove front method is also in linear time. And the reason is that when we take out that 0th index, all the other items that are in the list have to shift one index to the left. Let's make a note about that. The runtime is linear, or O of n, because when we remove an item from the 0th index, all the other items have to shift one index to the left. Let's work on the docstring for remove rear. This simply removes and returns the last item of the list. And that side of the list represents the rear of the deque. The runtime for this is constant time because anytime you index to the end of a list, that's done in constant time. There's one thing we didn't account for in either of these, and that is what happens if we try to pop a list that doesn't have anything in it yet. We can add a check for that condition by simply saying if self.items, which means if there are items in that list, we're going to pop. Otherwise, we'll just return none. And I'll add that logic down here as well. Exactly the same. Otherwise, we'll return none. Now our remove front and remove rear methods are complete. Let's code out the logic for our peek front and peek rear methods. It'll be very similar to the remove front and remove rear, but instead of actually removing the items, we just want to see what they are. So to do that, we can say return self.items, and we can simply specify the index at which the item exists that we want to see. So the front of the deque, again, is represented by the left side of the list. So the leftmost item in the list is going to be at the 0th index. Now, it may be the case that we try to call peek front on a list that doesn't have anything in it. So let's account for that now, and we'll just say, as long as there are items in the list, show me that leftmost item. And if the list is empty, we'll just return none. Peek rear is going to be nearly identical, so all we're going to need to change is that index. We'll say if self.items, meaning if there is something in the list, return self.items at the -1st index. This will always give us the last item in the list. And if the list is empty, return none. I'll save that and go back to the terminal to run the file. First, I need to create my own deque object. And I'll add a couple items into it so we have something to peek at. But first, let's call each of these methods and see if we handled appropriately the case where there's nothing in the list yet. Cool, that returns none. Let's do peek rear, and that also returns none. Now I'm going to go ahead and add some items in here. So we'll just do add front, I'll add apple, And I'll add one more. Let's do banana. And let's just make sure of their positions. So bananas on the left, apples on the right. So if I do peek front, it should show me banana. Let's do my d.peek front. And that's what we get. We can look at the items again just to make sure that we didn't remove anything unintentionally. We did not. So now let's do peek rear, and this should show us apple this time. Great. And let's check the items one last time. We're in good shape. So let's go back to the code and add a docstring and a note about the runtime. So peek front returns the value found at the 0th index of the list, which represents the front of the deque. The runtime for this is just going to be constant time because all we're doing is indexing into a list. And likewise, the runtime for peek rear will be the same. So we'll say the runtime is constant because all we're doing is indexing into a list. And I'll go back here and make my note about what the function is actually doing. It simply returns the value found at the -1st or last index. And I see I've got a typo up here in the peek front docstring. We'll fix that. There we go. So now we've completed our peek front and peek rear methods. Let's code our last two methods for the deque class, the size method and the isEmpty method. These are logically identical to the size and isEmpty methods that you might use for a stack or a queue. For the size method, all we need to do is find the length of the list that is representing our deque. And to do that, we can use Python's built-in length method. So we'll simply say return the length of self.items. And even if items is an empty list, this will still return 0 for us rather than erroring out. For the isEmpty method, all we need to do is compare self.items to an empty list and return that value. What this expression should give us is a Boolean, and note here we need to use double equals, not single equals. So if self.items is an empty list, this should evaluate to true, and if self.items is not an empty list, this should evaluate to false. Let's save this and try this out in the terminal. I'll create our own deque object. And let's try this new isEmpty method now that we've just created the object and haven't added anything to it yet. Cool, so we get true, which is what we would expect. If I go ahead and add something, we should get false if we run that isEmpty method again. So let's add apple, and then let's call the isEmpty method, and we get false. Great, so that works exactly as we expect. At this point, if I do my d.size, I should get 1 because we've only added one thing to our deque. And that's what I get. Let's go back to the code and create our last couple docstrings here. The size method simply returns the length of the list, which is representing the deque. The runtime will be constant because all we're doing is finding the length of a thing and returning it. Now we come down to the isEmpty method. And in summary, what this is doing is it's checking to see whether or not items is an empty list. Checks to see if the list representing our deque is empty. And it returns true if so, or false if it isn't. The runtime here is also constant because all we're doing is running a Boolean check and returning that value. And now our whole entire deque class has been coded. Let's practice some problem solving using the deque data structure. The prompt for this challenge is to use a deque data structure and write a function that takes in an input string, The function should return true if the string is a palindrome, or false if the string is not a palindrome. As a reminder, a palindrome is a word that is spelled the same backwards and forwards. Some examples would be mom, level, and kayak. So give this a try, and I'll come back and show you how I approached it. While there are, of course, many approaches you could have taken to solving this problem, I'll share with you what I decided to do. I knew that I would have to loop through the input string and add all of the characters to the rear of the deque to get them into the deque. I chose to add each item to the rear of the deque because adding an item to the rear of the deque is a constant time operation. As long as the deque's size is greater than 2, I would remove the frontmost item and the rearmost item from the deque and store each of those in their own variables. If those two variables aren't equivalent, I would return false right away. If the two variables are equivalent, though, then I could proceed to the next pair of items. If the size of the deque eventually gets to be smaller than 2, meaning there's only 1 or 0 characters left in the deque, then I know the string is a palindrome, and I can return true. Now let's talk through how I implemented this in code. Now I'll show you the code I wrote to solve this problem. I knew that I had to use a deque, and I implemented the deque exactly the same way that we did earlier in the chapter, so I won't go through that here. Instead, I'll move on to the function itself. I created a function on line 22 called checkPalindrome. It takes a parameter called inputString, and that's the string we want to check whether or not it's a palindrome. On line 24, I create my own deque object called my_d. And for every character in my input string, I add that character to the rear of the deque. This preserves the order of the characters as they're present in the input string. On line 28, I start my while loop. As long as there are at least 2 items in my deque, I want to continue removing items from each end and comparing them. I do that by calling the removeFront method on my deque on line 29 and store that in a variable called frontItem, and I do something very similar on line 30 where I call the removeRear method on my deque object and store that in a variable called rearItem. I then compare those 2 variables. If they're not the same, I can fail quickly and return false. If they are the same, I simply go back to the top of my while loop and do the same thing on the next front and rear items. If all of those iterations go well and I eventually get to a deque that has a size of 1 or 0, that means the string was a palindrome and I can return true. I wrote a couple test cases here at the bottom. The first one passes in an input string that has the word race car in it. This is a palindrome, and so I would expect the result of this function call to be true. The other test case should return false because the word oranges is not a palindrome. Let's go to the terminal and run this file. So again, I should get true and then false. And that's what I get, so we know that this works. Again, there could have been other ways you could have solved this, but this was the approach I took. Congratulations on completing the course! Now that we've worked through Python implementations of stacks, queues, and deques, be diligent about practicing. Choose to set aside an hour or so to practice these implementations on your own. To go even deeper, I recommend a few related LinkedIn Learning courses. The first one is called Python Essential Training, especially focus on Chapter 9, which is all about classes. The other course is called Programming Foundations, Object-Oriented Design. A high-quality external resource that I really recommend is a book called Problem Solving with Algorithms and Data Structures Using Python. It's written by Brad Miller and David Ranum and is available freely online. You can find the website at interactivepython.org. In addition to covering all that we covered in the course, like stacks, queues, and deques, it also touches on linked lists, other data structures, and even recursion. Thanks so much for joining me in this course. I hope what you've learned has increased your confidence and helped you prepare for your next technical interview. In addition to being a software engineer myself, I also coach other software engineers through the technical interview process to help them reach their own goals for career growth. To access more interview prep materials made especially for ambitious software engineers, or to inquire about personalized career coaching, visit my website at empoweredengineers.com. You can also connect with me on Twitter at empoweredeng or find me on LinkedIn.